Welcome back, everyone. Today we'll be talking about two-dimensional structural analysis. This lesson builds off what we learned in lesson 1, so go check that out first, and then I'll see you right here. In lesson 1, we modeled this beam using three-dimensional analysis, but if you're being observant, we didn't really need to use three-dimensional analysis for this case, and two-dimensional analysis is going to be both simpler and more efficient. So we're going to repeat the same problem in 2D here. Just like last time, we'll start in the workbench. Let's create a static structural analysis object. We'll just drag that out. Now, by default, our analysis type is three-dimensional or 3D. So if you click on geometry and you see over here on the right, we have analysis type 3D. Let's change that to 2D. So now my geometry and analysis will be a two-dimensional analysis. We'll leave the engineering data the same. That has our default structural steel material properties. So let's create some geometry. I usually prefer to do my two-dimensional models in the XY plane, having Z be my thickness. So let's specify that. I'm going to select my sketch plane, select XY, hit plan view so I'm looking at my plan. I'll create a rectangle starting at the origin. My beam last time was 2,000 millimeters long, and I see that my units have reverted to inches. So just as a review, changing units, file, space claim options, units, and metric. So now we're back in millimeters. Hit OK. I'll create my rectangle now. It's 2,000 millimeters. I'll hit tab by 200 millimeters high, tab, enter, and there I've defined my geometry. So I'm going to return to 3D mode. And just like last time, I want to have a loading surface right here in the middle. That loading surface was 200 millimeters wide. So I am going to split my body here, and I'm going to split it at 900 millimeters from that end, and then another 200 millimeters from here. And you can always check. You can go to measure here, measure that distance. That line is 900 millimeters long, and that line is also 900 millimeters long. So now I have my loading surface right at the middle, and I'm ready to go. So once your geometry is defined, you don't need to save this unless you want to use this geometry for another project. I'm just going to close, and it's automatically going to go over to ANSYS Mechanical. Now here's our model in ANSYS Mechanical. So you can see it's already in the 2D plane, just presented in XY. The first thing that I'd like to do is check my geometry. So if I click here on geometry, we can see what type of 2D behavior is assumed for this analysis. By default, that's set to plane stress. So you can change this from plane stress to axisymmetric plane strain or other options. We won't discuss those here. In this case, plane stress is the correct type of analysis. Plane stress means that there is zero stress in that Z or out of plane direction. And that's effectively true for beam bending. So let's select plane stress. I'll click on my surface object here. We'll notice by default, the thickness of that object is 1,000 millimeters or 1 meter. In reality, we have 100 millimeters, so let's change that to 100 for the thickness. Just to illustrate some of the options for the other cases, if I select, for example, axisymmetric, then my cross-section that I've drawn here will be rotated about my y-axis. So my y-axis is wherever you happen to draw it. Right here is my origin. So my section would be rotated around that axis. That's useful for shafts, cylinders, things like that. You can also consider plane strain analysis. For plane strain, this would be most often for something that's infinitely thick. You would have zero strain in that Z direction, although there could be stress in the Z direction. With axisymmetric and plane strain, you'll notice that there's no thickness setting because thickness is irrelevant in those two analyses. You can only specify that for plane stress. So let's change this back to plane stress because that's what I actually want to use. Double check. Yeah, it didn't change my thickness, so I'm ready to go. My materials are set. They're just default. So now let's create a mesh. So I want to create a sizing first. And first, I'd like to select my geometry. If you just click around, you'll notice it's just going to select one of these things at a time. Hold Control down to select multiple objects at once. So now I've selected the entire part. I'll apply that. So I'm applying my sizing over this entire body. And I'll set my element size by default to 50 millimeters. So same as last time. I'll generate a mesh. And you'll notice the meshing looks a little bit strange, and it actually gave me a warning message down there. It doesn't look perfect, which is a little bit unusual for something so simple. So a quick way to sometimes fix this is to give it a new method. So let's click on method now. That controls your meshing algorithm that it uses to generate your mesh. I'll select here. You can't really easily see what I've selected because my mesh is still on. So let's turn the mesh off. I'll click show mesh here. All right, and I see I've selected my entire plane here, so I'll apply that. And by default, it's going to use this quadrilateral dominant mesh. I found just with experience, multi-zone quad tri tends to give you more regular meshes for these nice shapes. So let's use multi-zone quad tri and hit solve. And it will once again generate my mesh. Actually, I shouldn't have hit solve, so you'll see what actually happened. I should have hit generate. Solve does generate your mesh, but then I don't have a proper solution yet, so it gave me a brief error, which is not the end of the world. You can see I still have a mesh here defined, and it actually looks much nicer. So meshing is done. We're ready to dive into defining boundary conditions and forces. So click on static structural. Let's put a fixed support on an edge on this right side, and I'll hit apply, and I'll do a second fixed support on my left edge, hit apply, and then I'll apply a force to this top loading surface, hit apply, and our loading is 20 kilonewtons down, so I'll apply this as components. Only need to define x and y here because it's two-dimensional. So negative 20,000 newtons acting down. Now we're ready to go. So now if I hit solve, it won't give me that error message, and it should run my analysis pretty efficiently. All right, and it's actually done. So let's see what it did. I'll click on solution here. For my results, let's look at a total deformation. Let's look at an equivalent von Mises stress and the normal stress, which by default is in the x-axis. That's the one I want here. I'll hit solve. Again, that won't redo your entire analysis. It's just going to generate those results from your previous solution. So here I can see my normal stress. I can probe it at mid-span here, and it's about 7 megapascals there in compression and about 6.7 megapascals in tension on the bottom. Effectively the same numbers that I saw from my three-dimensional analysis. Now let's dive a little bit deeper into the results. Let's say I want to look at my reaction forces at the right and left ends here. How do I do that? Let's click on solution again. And we'll go over here to probe. And this allows you to probe specific locations for specific outputs. So I can get a force reaction or a moment reaction. So let's click force reaction first. And I can select which boundary condition it's going to compute that at. Force support, or fixed support, excuse me, is my reaction at the right side. I'll create another force reaction for my left side, that's fixed support 2. And then I'll create moment reaction for 1 and moment reaction for fixed support 2. And I will hit solve. So here we can see the results. On the graph, it just presents as a vector. So for this moment, that vector is coming out of the plane in the z direction. I can see my result for my z-axis moment is 4.9 times 10 to the 6 Newton millimeters. So that's about 5 kilonewton meters. We can see similar results for my force reaction. In the y-axis, it's 10 kilonewtons up. And there is actually a resultant force in the x direction. That's because this beam is elongating slightly once being deformed. So there is a x resultant force on both sides, self-equilibrating. Now let's say I'm interested in some results at a specific cross-section. Say, for example, my normal stress is in the x direction along this cross-section right here. So I can always probe those results, and it works, but it's not the best way of always doing it. I can probe specific points, but it's really just where as accurate as you can click. So useful for getting a rough idea, but maybe not exact if I want to, for example, take this to a chart in Excel or something. So instead, let's define a path over which I'm going to output my results. So to define a path, we'll scroll up here, we'll go to model, and we'll create construction geometry. And we'll make a path. Now the path needs a start point and an end point. You can click on certain points in your diagram, or you can just type in the coordinates. I know where this is. So I'm going to start at 1000 in the X and 200 in the Y. So I'm starting on top there. And I'll end at 1000X and 0Y. So here's my path going from point 1 to 2 in the direction illustrated by that purple arrow right there. I like to rename my paths. So if you right click on path, you can go to rename, or you can hit F2. Let's call this midspan. That's useful if you have multiple paths over which you're looking at results, then you'll actually know which one is which. Now that we have that path, we'll scroll back down, go to our solution, and let's say I wanted to define a normal stress along that path. So again, normal stress in the X direction. Now, how I select where that normal stress is computed is by this thing called the scope. So by default, the scoping method is all bodies. So that's everything. And it gives us that diagram that we see here with all the contours. For the second case, I only want it along my path. So I'm going to change my method from geometry selection to path. And I'm going to select which path I want. I have one, it's midspan. So I'll click that. And that should be ready to go. So now I can hit solve. And we can see the results. It doesn't give me a contour diagram except along that path. And I can pull up this bar here to see the plot of my results for the stress through that cross section. So again, this is going along the path on the x-axis. So 0 is the start of your path. That's point 1 here. 200 millimeters, that's the end of my path right there. And you can see I have tabular data for this entire thing. So if you want to, for example, save this to Excel, I can right-click, select all, and then right-click again and export that. And then it will allow me to export these results to an Excel document. In this case, I've done this for 1 through 49 points. Maybe that's a little bit more than I really want. You can change that on your path definition. So if I scroll back up here and I go to my path definition, the sampling points is the number of points along that path, not counting your endpoints. So in this case, I have 47 sampling points plus the 2 endpoints. So that's how it got me to 49 points. Let's change this to 8, for example. So then it's going to have 8 points along the line plus the endpoints, so 10 total points. I have to reanalyze my normal stress because it's going to pull the values at those different locations. And here I have my 10 points through my cross section. And so again, if I want to export these to Excel, I can select them all, right click and export. And that is all for today. So please subscribe and I'll see you next time.